In this video, we'll talk about the use of the finite element method to solve a one-dimensional differential equation. So the situation will be as follows. We will have a one-dimensional problem domain. We'll assume that the left edge is at x equals 0 and the right edge is at x equals L, and we have nodes, and these nodes do not need to be equally, but we have nodes along the problem domain, including nodes at the endpoints. Now we will need to number any node that is associated with a point where the unknown, where the quantity to be solved for is unknown. But we don't need to number, we don't have to have a weight coefficient that is treated as an unknown where the quantity is known. I know that's pretty vague, so let me try to explain that in more detail. Okay, so suppose that our differential equation is something like this: d squared y dx squared plus p dy dx plus qy is equal to 0, with the boundary conditions y of 0 is equal to a, and maybe y of L equals b. Well, in this case, what we want to solve for, of course, is y, and in this case, since y is known at x equals 0 and also at x equals L, then we don't have to, we can take advantage of that right away. And so for instance, if we do the usual first step here and we expand y in terms of basis functions, we could say that we would normally write something like this: y is equal to the sum I equals 1 to n of ci times bi of x, where the different bi's are basis functions. Now, in this case, you have to decide where you start the numbering, and in this case, since y is known at 0 and since y is also known at L, we don't have to start numbering here at x equals 0, and we don't have to stop numbering at x equals L. We can start numbering at this first node right here, and we can stop numbering over here at this node. Now that doesn't mean that we don't need basis functions at x equals 0 and x equal L. We would need basis functions there, and we would need weight coefficients, but they are known weight coefficients. On the other hand, let's suppose that instead of having these boundary conditions, y of 0 equals a and y of L equals b, suppose we had y of 0 equals a and y prime of L equals b. Well, in that case, we don't know y at L, and so then we would need to number from the same first node over here, shown here, but then we would stop numbering at x equals L. So I think that this will become clearer as we proceed, and for right now I'll go with the easiest case, which is with two Dirichlet boundary conditions. And so we'll have unknown coefficients at all of the interior nodes, But at the exterior nodes, the ones on the boundaries, we will have known coefficients. And so this means then that y is equal to, we could write 0 as maybe something like this. A b0 of x plus b n plus 1 of x. Now, remember that the way that these basis functions go is that bi of x has value, well, let's say like this, it equals 1 at node I and 0 at all other nodes, and furthermore bi of x is 0 everywhere except between nodes I minus 1 and I plus 1. Between, well, actually, let me just, it'll be easier to, so for instance, if this is node I minus 1, and this is node I, and this is node I plus 1, then bi would look like this. This is for first order basis functions. Now, later we can talk about higher order basis functions, but for a first order basis function, this is what they look like. And this has a value of 1 here at node I, and it varies linearly between 0 and 1, from I minus 1 to 1, and then linearly from 1 to 0 as you go from node I to node I plus 1. Then everywhere else it would be 0. So with that knowledge of the basis functions, and you can come back up here to our expression for y, and you can see that it will automatically agree with the two boundary conditions given. Now, what I would suggest is that rather than writing y in that way, you write it a little more compactly like this. Write it as the sum I equals 0 to n plus 1 of ci bi of x, where it's known that c0 is equal to a and c n plus 1 is equal to b. So that's the expression that we will go with for the rest of this discussion. So let's substitute that expression for y into the differential equation, and then we can proceed with this discussion. So again, our differential equation is d squared y dx squared plus p dy dx plus qy is equal to 0. And later on, we can do problems with forcing functions as well. That's no problem. It's no difficulty. And y is equal to the sum I equals 0 to n plus 1 of ci bi of x. And so we go ahead and substitute that expression for y into the differential equation, and we will get ci times the sum I equals 0 to n plus 1 of d squared bi dx squared plus CIP times the sum I equals 0 to n plus 1 of dbi dx plus we can't take these CI's outside of these summations because the summation is a summation over I, so we have to leave that inside. CI, and then here Q times the summation I equals 1 to n plus 1, and that should be 0, of CI BI equals 0. So if we look at this for a moment, we can write this a little more compactly in the following way. We can have this as the summation I equals 0 to n plus 1 of CI times d squared BI dx squared plus p dbi dx plus q bi is equal to 0. That's a more compactly written form of the previous line. And actually, just for convenience here, I'm going to change the index from I to J. Of course, we could use any index we want, but I'm going to change this to J. So here's J, sum over J, and then this is BJ, BJ, and BJ. And I'm doing that mainly because this is a more traditional way of writing this. Because then, since we're talking now about the weak formulation, we will now multiply both sides of this equation by Ti, which is a testing function at node I. And we're going to use Galerkin testing, which means that Ti of x is equal to Bi of x. So if we multiply both sides of that equation by Ti of x, we will get the sum j equals 0 to n plus 1 of Cj times Ti of x multiplied by d squared Bj dx squared plus p dBj dx plus q bj is equal to 0. And now we will integrate both sides from 0 to L and see what happens. So when we do this, we will get sum j equals 0 to n plus 1 of Cj integral from 0 to L of Ti of x d squared bj dx squared dx plus integral 0 to L of ti of x dbj dx plus, and let's see, we have a p here, plus q times the integral from 0 to L of ti of x bj of x dx is equal to 0. Now, when we look at the integrals in the brackets, the last integral here certainly doesn't provide any difficulties because remember ti is equal to bi, and so we just have a linear function times a linear function, and that would not be any problem at all to integrate that. And likewise, now when we look at the middle integral, that would be even easier to integrate because dbj dx, since bj is linear, that would be dbj dx would just be a constant, so that will be easy to integrate. But for this last term, we don't necessarily want the d squared bj dx squared term appearing there because of the delta functions that would arise. And so what we can do there is use integration by parts. We will let u equal ti, and we'll let dv equal d squared bj dx squared dx. And so this means that du is dti dx dx, and v is equal to dbj dx. And therefore we will get summation j equals 0 to n plus 1 of cj and then we'll have uv from 0 to L, so we'll have ti dbj dx from 0 to L minus the integral from 0 to L of v to u. So we have dti dx dbj dx dx, and then we have the rest of our integrals plus p times the integral from 0 to L of ti of x dbj dx dx plus q integral 0 to L ti of x bj of x dx equals 0. Now let's look at this first term here. right here. And what we will realize about that term is that it is equal to 0, because the reason for that in this case is that at the two endpoints, remember, at the two endpoints, y is known. Y of 0 is equal to A, y of L is equal to B. And so since y is known at the nodes, the two end nodes, you don't need to test at those nodes. Now again, you will need basis functions at the two endpoints, but you don't need to test at those two endpoints. So the first the first testing function you will have will be the one associated with node 1, not the one associated with node 0. And likewise, the last testing function that you have will be the one associated with node n, not with node n plus 1. So this means that all of the testing functions, it doesn't matter which one we're considering, all of them will go to 0 at both x equals L and at x equals 0. In every single case, it doesn't matter which one of those n testing functions, T1, T2, up to Tn, it doesn't matter which one you pick. All of those testing functions, since they are identical to the basis functions, they go to 0 at x equals 0 and at x equals L. So the first term here will simply disappear. That's 0. And therefore, we now have summation j equals 0 to n plus 1 of Cj times minus the integral from 0 to L of dti dx dbj dx plus p integral 0 to L of ti of x dbj dx dx plus q times the integral of 0 to L ti of x bj of x dx is equal to 0. Now, let's, to make this look a little bit better, let's do the following. Let this term in the brackets, we're going to call that Mij. So this equation then, when we do that, it becomes very simply just summation j equals 0 to n plus 1 of Mij Cj is equal to 0. Now remember that C0 is equal to A and Cn plus 1 is equal to B. So what we will do now is we will finally, now that we have done all this work, let's do the following. We will say then this is the same as saying M I0 C0 plus m I n plus 1 c n plus 1 plus sum I j equals 1 to n. Since we have taken care of the first term and the last term, now our summation goes from 1 to n of m I j c j is equal to 0, and therefore sum j equals 1 to n of m I j c j is equal to minus m I 0 times c0, which we've already said is a, minus m I n plus 1 times b. Now, this is a single equation. This is one equation in the n unknowns C1, C2, ... Cn. Keep in mind that the m's are not unknowns. Here again, right here, this term in the brackets is the expression for mij, and everything in there is known. I mean, you have to calculate it, but it's known. It's easy to, it's straightforward, maybe tedious, but straightforward to calculate. So the m's are not unknowns, and a and b are your boundary conditions, so they're not unknowns. The only thing in this equation that's unknown are the values of Cj from 1 to n. So this is one equation in the n unknowns. And now if we let I, so let's just say, if we let I vary from 1 to n, we get n equations in n unknowns, which can be written in matrix form and solved. And that's how we use the finite element method with a Galerkin testing and a weak formulation to solve a 1D finite, to solve a 1D differential equation.